Okay, so in the previous video, we computed something called a t-statistic. You can see it right here. We ended up with a value of negative 1.27. I'm going to call that t-observed. I told you that that previous video was all about trying to figure out something. We were trying to figure out if the difference between group A and group B, the difference between their averages, was something that we would observe by random chance alone. Right? And if it's not due to just random chance alone, then we might say something like, oh, well, this is meaningful and we have confidence this is real. So, but we ended up with this weird value, a t-value, and it doesn't look like anything that would be like a percentage or a proportion, something that might represent like a probability level. So we need to look up something called a probability level. And to do that, we need to have more information than just that number. We need to know something called the degrees of freedom. And the degrees of freedom is going to change depending on how many people are in your study, right? If you have more people, that should give you more confidence, right? That what you saw might be real. And also it's going to depend on the exact type of statistic that you're computing. In this case, we computed an independent samples t-test, also called a two-group t-test or two-group t-statistic. So in this case, the degrees of freedom is equal to something called, I'll highlight it yellow here, k minus 1 plus k minus 1, and that is k represents the number of people in each group. So k for group A, k for group B. We had 10 people in each group, and so 10 minus 1 is 9, and so 9 plus 9 ends up being 18. So our degrees of freedom for this test is 18. And you'll have to go with me on blind faith at this point as to what degrees of freedom are and why they are used. There will be a very quick explanation video coming up where I give you sort of a conceptual explanation as to why that is. But for now, just go with me on blind faith. Our degrees of freedom for this test is 18. And so we know our t-value, 1.27. We could ignore the negative sign, and we know our degrees of freedom. And so let's go to a t-table. A t-table is something that, this is how people used to figure out what their probability values were. By the way, the probability value, we're gonna use the term p-value from now on. And if you guys have taken stats classes before, then you're probably familiar with p-values. Here is a refresher. So you probably can't see these exact values in your video right now, so you'll need to open up your PDF file in all likelihood. But you can see that we have different values in the rows and columns. So notice you see cumulative probability, one-tailed and two-tailed. For now, I want you to just pay attention to this row that says two-tailed. We only need to focus on that. I don't want to focus in on these other things right now. And I also see that there is something called degrees of freedom. All right, so remember our degrees of freedom was 18. So I'm going to highlight the row here for degrees of freedom 18, highlight most of that row. And so this table is of t critical values. So we call these t critical values. And then this one, remember, is our t observed value. So let's see if we can find a t critical value that is close to our t observed value in this row for degrees of freedom 18. Okay, if I scan over, I can see that we go, let's see, 1.067, 1.330, 1.734. Now, there is no 1.27. But there is a 1.33, which is pretty close to our 1.27. So I can look up in this row here, and that corresponds to a p-value. Again, this is a probability value. We're going to call it a two-tailed probability value of 0.20. What does that 0.20 mean? What that means is because we're being approximate here. 1.27 doesn't exactly equal 1.33, it's just really close. So we're going to say approximately. There is an approximately 20% chance that this value that we observed, the difference between the two means, was observed just due to random chance alone. So you could also say that in a different way. That is, if we conducted this same two-group study that we did, and we conducted it 100 times with different groups of people every time, then about 20% of the time we would see a difference of that level, even if there were no real difference between the two groups out in the population at large. So basically, the bigger our probability level, the less confidence we have that our result is real. And the lower this p-value, right? If we had a p.01, that would give us a lot more confidence that the difference we're observing between the two groups were real. Because it's saying, right, if that's really low, say it's 0.01, well, that's saying there's one, that's saying that if we conducted this study 100 times, only once would we see a value this large if there were some sort of, if this were just due to random chance. So that's low, and so we can say, oh, well, it's probably something real. Or at least it gives us more confidence that it's something real. There is a standard, and the standard is to use a 0.05 value. That is the standard that's used in academics. People will say, okay, it's an arbitrary thing. There's really not much of a difference at all between, say, 0.04 and 0.06. But for whatever reason, tradition and history has chosen 0.05 as like a threshold cutoff. And so what you really do, the correct procedure is to go, okay, I found my 0.05, I go down to degrees of freedom 18, and that tells me that I need a t observed value of greater than 2.101. We need a value greater than that in absolute value to have confidence that the difference between these two groups is real. So that's how we get our p-value, our probability value. And lucky for us, Microsoft Excel does something for us. It'll actually compute a p-value for us. And so this is negative 1.27, so that's even lower than 1.333. So that means our p-value should probably be slightly higher than 0.20. So if we go over here to our groups, I'm going to clear these contents out so we're unnecessary, and we just use the function t-test, and we put in the values for group A, and we put in the values for group B, and we specify the number of tails. Remember, we're doing a two-tailed test here. And the type, we're wanting to do an independent samples t-test, and in Excel that's represented by the number 2, close parentheses, and press go and see what happens, and we end up with a p-value of 0.219. Again, the way we can interpret that is that if we did this study 100 times, and in reality there was no difference between A mean and B mean, they were exactly equal out there in the population. But if we did this study 100 times, pulling, 10 people for each group every time we did the study, we would get a difference this large, 21.95% of the time. So a quick way to say what the p-value is it's your false positive rate. If you do this study over and over and over again, many, many times, you're going to have a certain number of false positives. If you're assuming that there is no result, if you're assuming there is no difference in the population, any positive result you get is going to be a false positive. So in this case, this would be your false positive rate. For short, we'll call it the p-value, and we'll encounter that p-value again a few times this semester. So that's why I wanted to kind of over-explain it. So that is how you get the probability value from the t-statistic, and it's going to be a very similar procedure for most test statistics. And that p-value, by the way, is going to be interpreted the same way. It's going to be interpreted as your false positive rate. It's interpreted the same way regardless of which type of statistic you're computing. So you can continue to use that knowledge as we progress through the course. I will see you soon.